Hello, it's Mr. Kaladi here, and today we are doing our last lesson of this first unit. It's the applications lesson. So we're going to look at take what we've learned and look at some real-world problems. This is an important section because most of the IB exam is very abstract. If you are going to see a real-life question, often it is related to exponents or logarithms. So let's start with this example 1. There are 100 bacteria in a colony, and the size of the colony doubles each day. This idea of doubling, that should be your giveaway that something exponential is happening here. Remember the penny question, exponential, the doubling of the penny. That tells me it's exponential. Then the question is asking us to model the growth of the colony as a function of time. Model, this is a key word. That means find an equation, a mathematical model. Think about a weather reporter trying to model the weather. They have all these equations that then allow them to predict the weather. So what I would suggest, if they're not giving you the equation, you have to make it up yourself. It really helps to make a table to help think the problem through. So we have time, right, as a function of time. So time is kind of my x-axis. I'll call it t, and it's measured in days. And then I have population. We'll call it p, and that's the number of bacteria. Let me get a ruler here. Make a nice table for you. So we have x and y, or t and p in this case. Okay, so we start off with a population of 100. So I'm going to call that times 0, the start, right at the axis. Now, we double every day. So after one day, how many bacteria do I have? Well, I have 100, and I doubled it. I multiplied by 2. 200. After, on the end of day 2, it's doubled again. So I've taken this number, 100 times 2, and I've multiplied it by 2 again. Day 3, I have multiplied that number by 2 again. I think by now you can see the pattern. This is why it's helpful to have a table. On the 4th day, I'm just multiplying by 2 4 times, so to the power of 4. So now, if I wanted to model it, I want to make a mathematical number. Well, I can tell you the population. The population is 100 times 2 to the power of 1 for day 1, 2 for day 2. So it's just whatever day it is, that's my exponent. And that's my answer for part A. Part B, sketch the model. Well, this is, if you think about it, this is something I can do. This is just an exponential graph that's been, has some transformations applied to it. The 100 in front is a vertical stretch, right? So someone has just stretched my graph. But that does, as we know from graphing transformations, it doesn't make a huge difference because the exponential graph, so this is P, and this is T. Usually the graph goes through 0, 1, but in this case we've stretched it vertically by 100, so it's going to go through 0, 100. I mean, you technically knew that from your table too, right? You could have just used your table to find that intercept. We know that there's an asymptote going this direction, and then we have this explosive exponential growth. Again, you don't need any other points. You just need to show that explosive growth. And there's my asymptote. Be careful with the question. I mean, the negative time is impossible, so this is not really relevant to our question. Sometimes the question might say, sketch the model for t is greater than 0, so then it would be, you wouldn't even sketch this. It wouldn't be included. And there's that population growth. Okay, so now how many bacteria in the colony after 2 weeks? Well, now I can use my model to make a prediction. 2 weeks is 14 days, so I'm going to sub in t equals 14. So p at 14 is equal to 100 times 2 to the power of 14. I'm going to need a calculator to do that. I definitely can't do that one in my head. 2 to the power of 14. Oops, no. 2 to the power of 14 times 100 is 1,638,400 bacteria. So those 100 bacteria have really gotten big. And again, that's the whole thing with exponential growth. It's really hard to even fathom how fast it is. And that's how you're able to make an equation even when you're not given, you're only given some information. It helps to have a table. Okay. One area where IB likes to give exponential type word problems is related to money. Now in MCR, in your previous course, you've looked at, you would have done a financial math chapter, hopefully. So maybe this is sort of familiar. We can use the same reasoning that we did above. We can make a table, though, to help us. So you invest $850 into a savings account that pays 4% interest per year. Dream on. Interest rates right now are about 1% or less. But in this question, 4% per year. How much money will you have in your account at the end of 5 years? So anytime you see interest, compounding interest, this is an indication that it's exponential. Right, that's the key word that tells you this is not quadratic, it's not trig, it's exponential. How much money will you have at the end of 5 years if the interest is compounded annually? Okay, annually means I get money every year. Let me try to understand this question using a table. So I'm going to make my chart. I have time in years, and I have the amount of money I get. I'm going to call that A and measure it in dollars. So we start off with $850. That's my amount at the beginning. That's a times 0. Now, how much money do I have at the end of 1 year? Well, I have $850 plus the interest. How much interest did I earn? Well, 4% per year. So I got 4%. 4% of 850. So in other words, I have 850, that's how much I have in my account, plus 4% of 850, so 0.04 times 850. If you want, the other way you could write this is you could actually factor out the 850, so you'd have 850 times 1 plus 0.04. And that's at the end of first year. Now, we don't care about first year. We want to know how much at the end of 5 years. Well, let's look at year 2. So at the end of year 2, I have $850 in my account, multiplied by 1.04, right? That's what I have from last time. If you want to check this with your calculator, you can, right? 850 plus 850 times 0.04, that's 884, right? I made a little bit of money. Or we could have just used, when we factored it out, we have the shortcut, 850 times 1.04. Now, that's how much money is in my account at the end of the first year. But then I earn interest on this, the second year, times 1.04. So I have even more money in my bank account. This is the idea of compounding interest. You're earning interest on interest. The rich get richer. So at the end of the second year, I have the amount I made the first year multiplied by that interest rate again. 1.04. At the end of year 3, I take the amount I have from last year, which is this long string. It's like 900 something. And I'm going to multiply that by interest rate again, 1.04. So I hope you can see the pattern here. On year 4, I'm taking 1.04. Instead of multiplying it by itself 3 times, I'm going to multiply itself by 4. So I would then say that you have the amount of money in your account. I figured it out now. It's 850 times 1.04 to the power of t. Right, where t is the number of years. So in year 3, if you want to figure it out, you're going to sub in t equals 3. Now in this case, we want to know how much do you have at the end of 5 years. So you sub in t equals 5. So you have A5 is equal to 850 times 1.04 to the power of 5. Let's do that with our calculator. 1.04 to the power of 5 times 850. That gives you 1,034.15. Wow, that's great. Look at all the extra money you made that you can use to buy a new video game or whatever. Okay, and see how we were able to build this equation using a table. So that helps us model, helps us make equations. Okay, part B. How would this change if the interest was compounded quarterly, meaning every 4 times per year? So 4 times per year, we receive 1/4 of the interest. So it's not like we get 4% every year, or 4 times a year. This means we get 1% at the end of March, 1% at the end of June, 1% at the end of whatever, September, and then 1% at the end of December. So that's how quarterly works. This is a real thing. We've already learned that the more frequently you compound your interest, the more money you make. So we can assume that this person is going to actually make more than this person. Let's see. Let's make a table. So this time I have my time, t years, and I have my amount, which is A, and it's in dollars. So make a nice table. Okay, so the first year, I start with 850. Okay, let's look at a quarter way through the first year, so the end of March. This is when I get my 1%, right? 1/4 of the interest rate. So I have 850 plus the interest. So in other words, I have 850 plus 850 times 4% divided in 4. If you want to see that mapped out, it's 850 plus 8. Okay, let's do this first. 0.04 divided by 4 is 1%, times 850, so that's my interest, $8.50, plus what was already in the account. So I have now in my account 858. I'm not going to show you that number. I don't care about the number, but I will factor out the 850 to help you build the equation. 1.01. Okay, so that's at the end of the first quarter. Now at the end of the second quarter, the end of June, you're going to get the next 1%. So it's going to be 850 times 1.01, which is what you got from the first quarter, times 1.01 again. 3/4 of the way through the year, you're going to do that again, right? You're going to have another 1%. So we're compounding more often, we're getting more interest on interest. At the end of 1 year, you're basically going to have done this 4 times. 850 times 1.01 to the power of 4. Now think about it. What about after 2 years? Well, now you're going to compound again March, June, September, December. So you're going to have compounded in total 8 times. After 3 years, you're going to have compounded 12 times. Let's see if we can make a formula, a general case. How can I predict the amount? Well, it's going to be 850 times 1.01. What's the relationship between this 3 and 12, 2 and 8, 1 and 4? Well, to figure out this number, the exponent, I have to take the year and multiply it by 4. So this is what my expression is going to be, 4t. So watch, let's sub in after 4 years. So, or sorry, after 5 years, at time 5. So then I'm going to sub in, so I have 850, oh shoot, 1.01 to the power of 20. Type that into my calculator, 1.01 to the power of 20 times 850. And that gives me 1037.16. Which account is better? The more frequent compounding is marginally better. That's $3. You can go buy a nice coffee. Now, this is something you can model yourself. You can build it with a calendar, or sorry, with a table. but it is something that's on our formula sheet. And let me just write out the formula so that you can you're familiar with it. So generally, for a compound interest question like this, let's look at the formula sheet. Compound interest is your future value, or the amount of money you have, is equal to the present value, the money you started with, times 1 plus r, where r is the interest rate in percent. Then you divide the interest rate by 100 to make it a decimal. And you divide the interest rate by the number of compounding periods per year. So in this case, we have we multiply, we divided the 4% divided by 4. That's how we got the 1%. And then you raise it to the power of n is the number of years, times k, the number of compounding periods per year. In our case, it was 4. So we used this formula. It looks really odd, but we still used it. So let's write it out, even though it's on your formula sheet. Future value, well, let's write it as a, just so that we can link the two. So a is equal to,
Miss Nieta, please contact the main office. Miss Nieta, please contact the main office. Thank you.
so a is equal, or your future value is equal to what you started with. We're going to call it P per principal. That's how I teach it when I teach it at the school. 1 plus r divided by 100 times, I guess we'll call it k in this case, which is what's on your formula sheet, to the power of kn. Where, oh my god, you can't see any of that. Oh, okay. A is equal to P times 1 plus R divided by 100k to the power of kn. So that's from your formula sheet, where P is the principal, I forget if it's AL, I always get confused. That's the starting amount. R is interest rate in percent. So that's why we divide by 100. We're turning the percentage into a decimal. And K is the number of compounding periods per year. So that is a formula we want to be able to use. Again, this is something I think IB tends to like, so I wanted to make it something that we looked at. So that's on formula sheet. More or less, a little bit different, right? Some of the letters are different. Okay, so there we go. That's our second example. Let's turn the page and we'll look at a third example. This is one that you might see in biology, a half-life question, or chemistry. Half-life is defined as the time it takes for a substance to decay to 1/2 its original amount. You'll see this for radioactive chemicals like plutonium, right? They're constantly decaying. The radioactive bismuth isotope has a half-life of 5 days. That means every 5 days, half of it's gone. There is 100 milligrams initially. Model the model the mass of the isotope. Well, model, I know from our previous question, means find an equation. And because it's half-life, it's dividing in half each week or every day, multiplying by half each time, well, that's an exponential sort of thing. So that tells me it's exponential. So if I'm going to model this, I'm going to use my strategy for modeling exponentials, which is to make a table. Right? They didn't give me an equation, so I got to figure it out myself. So I have time is the thing changing, and then time is the thing increasing, and then the mass is the y variable. Let me see if I can figure this out. So I start out with 100 milligrams. That's day 0. Day 1, day 2, day 3, I don't know really what happens here. Oh, day 5 is a half-life. So after 5 days, half of the mass is gone. So I've basically taken the 100 and I multiply it by half to get 50, right? Half of it's gone. Then 6, 7, okay, at day 10, it's going to half again. So whatever answer I had here, I'm going to half it. So 100 times half, which was 50, I'm going to half it again. Again, if you want to see this with a calculator, it is 100 divided by 2. That's what they have after 5 days. Divide by 2 again, 25, etc., etc. After 15 days, I have half times half times half. I think we see the pattern. After 20 days, I have 100 times half to the power of 4. So, can you make an equation for mass? Oh, you know what? I think we forgot to do something on the back page. Okay, we're going to go do it. Mass is equal to 100 times half. Okay, now how do I get 4 from 20? How do I get 3 from 15? Basically, I'm taking whatever my day is, and I'm dividing it by 5. So I have t to the power of 5. Or sorry, t divided by 5. Sketch the model. Well, we know this. This is a exponential decay graph. We know at 0 there's 100, so this point here is 0, 100. And we know that it's going downwards. In fact, you could look at it this way. This is t. This is 2 to the negative 1, right? So this is technically a reflection in the y-axis, right? That's what that negative is. That's why the exponential decay, when this is a fraction, is the same. You could just think of it as a transformation. So it's essentially an exponential that has been reflected. Again, the part over here is not really relevant because you can't have negative time, but you can it helps you draw the shape. Question. The bismuth isotope first drops below 10% of its original mass after n days, where n belongs to Z. Find the value of n. This is the classic style of IB wording because you know how to do what they're asking, but they're asking you in a strange way. So first of all, the bismuth isotope first drops below 10% of its original mass after so many days. Does it take 1 day? Does it take 2 days, 3 days? We don't know. When does it drop below 10% of its original mass? 10% of 100. I need to find out, right? Find the value of n. So all it's saying is sub in m equals 10% of 100. Of course, in math means multiply. So this means sub in when m is equal to 10. Okay, so here's my equation. So 10 is equal to 100 half t over 5. Now I have to solve for t. Oh, that's hard because this is now an equation where I don't know something that's in the exponent. Luckily, I just took an entire chapter on how to do these things. First thing I'm going to do is I'm going to divide both sides by 100. So that gives me 0.01. Sorry, 0.1. And I have half to the power of t over 5. Now, we looked at equations like this. How do you solve an exponential? Well, you can try to get the same base, or you can log both sides. So I'm going to log and log. What base will I choose? Probably 10, because that is on my scientific calculator. The great thing about logging both sides is now you can use your log law and bring the t over 5 down. So I have log 0.1, which is just a number, right? Let's not get lost here. Log 0.1, it's just a number, negative 1. And then I have t over 5 log of half, or log of 0.5. Now I can multiply both sides by 5 to get rid of the 5 here. So I have 5 log 0.1 is equal to t log half. And then I end up with, if I divide this out, I have 5 log 0.1 divided by log half. Let's use my calculator now. So I have log 0.1 times 5 divided by log 0.5. And I get 16.60964. So now what do I round to? Do I round to 16.6? Be very careful. They said they want to know the answer, or they're telling you that the number of days belongs to Z. This is one of my number families, and this is Z means integers. Right? You have whole numbers, natural numbers, integers. You have real numbers. I can go over all of this at some point with you, but Z is integer. So your answer has to be rounded to an integer. At 16.6 days, the mass hasn't dropped all the way to 10%, below 10%. That will only have happened when I go one day further, so 17 days. So that's kind of a tricky wording question, and it just comes back at the end. We have to do some tricky rounding. I believe I forgot back here to do part C, right? How long would it take to double the money if the interest is compounded quarterly? This is similar. Double your money, well, you started with $850, so double your money means you want to sub in an amount of 2 times 850, 1,700. So then I use my formula, which I have from here. So I have 1,700 is equal to 850, 1.01, and I'm trying to solve for t. This is hard, but not that hard because I've done a whole course, a whole chapter on this. I'm going to divide both sides by 850. Divide both sides by 850. So I get 2 is equal to 1.01 to the power of 4t. How do I deal with an exponential like this? Well, I log both sides. So log 2 is equal to log 1.014t. Now I can bring the 4t down, so I have log 2 is equal to 4t log 1.01. Now I need to get t by itself. So I have log 2 divided by 4 log 1.01. And now I can use my calculator. So I have, again, I use log base 10 because I can use this calculator, which I'm a lot faster with. I like it more than the GDC. Okay, and I get an answer of 17.415179, whatever. I got a round. Doesn't say anything weird here. It's just asking how much time. So the answer is always round to 3 significant figures. So 17.4 years. Wow. Maybe you can find a better interest rate. It won't take so long to double your money. That's convenient though if you are, saving for a car 17 years from now. Okay, last question. Is a word problem. I know you were waiting for it. A word problem related to logarithms. Now, exponential questions are more intuitive. So you might get a question where you have to make your own equation for exponents. It's unlikely you're going to have to make your own equation for logarithms. Usually for logarithms, if you're going to have a word problem, they're going to give it to you. They're going to give you the model. They're going to give you the equation. So that makes your life a lot easier. This question, after working in the area of study, students complete a test. Over the following 2 years, the same students were retested on several occasions. The average score was modeled like this, where t is the number of months after the test. So essentially what they found is that, you got 90% the first time, then 2 years later, then a few months later, you've gone down to 88. Then if you sub in t equals 4 months, you've gone down to 87. They can kind of predict what your mark is going to be based on how many months since you learned the material. So, pretty neat. Here we go. What is the average score of the first test? Well, the first test is the one you wrote, like the one we look at time 0. So we're going to sub in t equals 0. So I have s at 0 is equal to 90 minus 20 log 0 plus 1. So that's 90 minus 20 log 1. Log 1. You could shout it from the rooftops. What's log 1? Well, think about it. You could type in your calculator too. You don't have to think that hard. But 10 to the power of what gives me 1? Well, it has to be 0, right? That's one of those special cases. You might see it, you might not. You can always use your calculator if you have access to it. So 20 times 0, 0, so your average score is going to be 90. That's if you look at the first time they're tested. What is the score after 6 months? Okay, well, I'm going to sub in t equals 6. So s at 6 is equal to 90 minus 20 log 6 plus 1. 90 minus 20 log 7. Can't really do that in my head. I'm going to use my calculator. Log 7 times 20. 90 minus the answer gives me 73.098. I should round to 3 significant figures, so 73.1. So as you can see, students have really decreased 6 months later. This stresses us out, right, as teachers. Like, how am I going to get you ready for the IB exam if you forget things? That's okay, we all forget. Part C, how long should it be before the test is reissued if the average score is to be 80? So here I want everyone to get an 80, so I'm going to sub in s equals 80, so it's a different substitution. 80 is equal to 90 minus 20 log t plus 1. So in this question, I want to figure out what t is, how many months. Unfortunately, it's a log question, but luckily we just did an entire chapter on logs, so I'm going to subtract 90 from both sides. This gives me negative 10 is equal to negative 20 log t plus 1. Remember, I'm trying to solve a logarithm. I want to get log equals some number, so I need to do some more simplification. I'm going to divide both sides by negative 20. Do not divide by log, right? The only way to get rid of a log is to turn it into an exponent. This gives me positive half is equal to log t plus 1. Now we're in this great situation. To get rid of the log, I take the base, which is 10, to the power of half is equal to the argument t plus 1. So t, on the other hand, is equal to, in other words, is 10 to the half minus 1. Now I'm ready to use my calculator. So 10 to the power of 0.5 minus 1 gives me 2.16228. Or it's asking me how long should it be. It should be approximately 2.16 months. Be careful, but there was no real trick here, I don't think. They weren't asking you what month it was. They're just asking you how much time, around the 3 significant figures. Phew, so that is our word problems. Like I said, they might come up, especially the exponents. I find that is one that IB really likes. This is there's a bunch of questions in your textbook, page 133, number 1 to 5. Good luck, and we'll see you next time.